everybody. Thank you for being here. So my name is Giuseppe De Brusinis. I'm VP of Global Strategic Partnerships at Nanoprecise. And today we're going to talk about cloud-based energy center predictive maintenance on water pumps. Okay? It will all make sense, I promise, as we go through it. So very quickly on agenda about what to expect from today. We're going to go for a very, very quick company overview. And then we'll dive straight into the client case we'll present today. We'll talk about the challenge they experienced, the solution that we brought, and the outcome. So very quickly about Nanoprecise. We are an AWS partner, obviously, ISVA Accelerate partner. And we essentially help with three key problems, right? The first one is downtime. $600 billion are lost every year due to downtime. The second problem is that there is a 10 to 20% typical higher consumption of energy on rotational equipment that is due to maintenance requirements that are unaddressed. And the third one is that pretty much any company needs to produce more at the same or less energy to meet ESG goals. And so these are the three key problems that we help with. Now, the rotating equipment fundamentals, since we're focusing on rotating equipment, is that there's equipment, if the equipment fails, that impacts a business outcome. And if we can address that, we can create value, right? So to be a bit more specific, when we look at rotating equipment, these are some of the key industrial rotating equipment that we can monitor. So motor, pumps, compressors, turbines, blowers, etc. And so they experience faults somewhere along the way. Example, bearing faults, unbalance, misalignment, looseness, etc. Now, when these faults are encountered, the business outcome impact is increased maintenance costs, loss of production, loss of revenue, increased energy costs. So all of these are outcomes that are impacted by these faults. And so how can we create value? By reducing maintenance costs, preventing loss of production, reducing energy costs, etc., etc. This is just a framework to give you an idea of where do we start from. But the most important thing that we look at from our perspective is the lifetime cost of equipment is not just purchasing the equipment and maintenance when you look at predictive maintenance, but the power consumption. Power consumption is by far, especially on high horsepower machines, a very, very strong cost contributor. And so when we look at maintenance from the perspective of predictive maintenance and energy-centric insights, that's when you get what we basically focus on. That's why the name of the solution, okay? Energy-centric predictive maintenance for industrial rotating equipment. Examples, we've been helping companies getting over $200 million of savings, $10 million of savings for individual clients, and we keep growing as we go. But let's dive into the client case. So the client that we're talking about today is a large UK water utility provider that has 40 plus reservoirs, 300 plus water pumping stations, and 25,000 kilometers of water mains. Now, what is the challenge that this client was encountering? Essentially, they wanted to effectively monitor critical remote rotating equipment, right? And so, in this case, the equipment that they wanted to monitor are vertical pumps and horizontal pumps with a variety of high lift pumps, booster pumps, centrifugal pumps, and all they have in common that they are high horsepower motors, right? And so, some other challenges, part of this were water clearly is a key, vital public resource, right? And so the equipment downtime must be avoided at all costs, right? On top of that, slim profit margins, right? So the client was encountering slim profit margins. How do we deal with that? How do we deal with rising energy costs? And how do we deal with GHG emission goals? So when you put all of this into context, what you have is that there's pressure to both prevent the downtime of the water pumps, but also reducing energy usage, costs, and emissions. Right? So that is really the challenge statement. What is the solution to this set of problems for this client? What do we bring? And so our solution is an end-to-end solution that starts with a 6-in-1 IIoT sensor that captures 6 streams of data. It sends it to the cloud, obviously AWS cloud, where we have AI predictive analytics algorithms that do a full cycle analysis, which we'll touch on in a second, to deliver actionable insights that are available into a dashboard, via notifications, and also via APIs so that they can be used in a broader infrastructure context in the AWS environment and beyond. When you look at the more specific AWS reference architecture, you can see here the sensor that starts to send the data via either cellular or Wi-Fi, which we'll talk about in a second. The data goes into the SaaS deployment on the AWS cloud of Nanoprecise. You see that our models are there. You can see that because we are in the AWS environment, now all of that is easily available to create use cases across all the different AWS solutions. Especially if you're centered in S3, you can put those data in a Grafana chart. You can create Matterport visualizations with digital twins. And on top of that, you can use the API to also output it to ERP systems, data historians, CMMS. So this becomes fluidly integrated into pretty much your IT ecosystem. When you look at the sensor, particularly, it's a 6-in-1 sensor that collects 6 streams of data. So we have triaxial vibration, magnetic flux, temperature, acoustics, RPM, and humidity. Now, the raw data itself doesn't tell you much unless you're a certified vibration analyst, which reads through the charts. And of course, we want that, but we want to make sure that we create more value by automating some of the analysis. And so this sensor, as I said, sends data through cellular Wi-Fi. It then does a full cycle analysis where it does an anomaly detection. It characterizes the type of fault. It does the root cause analysis of it, and it prescribes a maintenance actions. That motor has a bearing issue. This is the cause. Go do this. Now, all of that analysis is done automatically and delivered as part of the insights that we offer. On top of that, we add analysis on energy cost change for that machine and the CO2 emission change for that machine. That's how we bring in the energy center piece into the predictive maintenance part. From a visual standpoint, the dashboard is very simple. It's a traffic light system. You have one plant, your equipment, right? Motor, pumps, gearbox, etc. If it's green, it means the machine is fine. If it's yellow, orange, or red, the machine has an issue. You can click into the machine and you start seeing, in this case, there's a BPFI issue, which is a bearing issue. And then underneath you see what are the potential causes already and what are in gray the suggested action. You can put this into a work order, your maintenance team can take it and go perform it, and that's how you automate the analysis of fault prevention, okay? Now, after that, this is how we trend variation of kilowatt over time. It's just an indicative chart to show you. We have a magnetic flux reading through the sensor, and the magnetic flux variations of the machine are directly proportional to the energy variation of the motor over time. So we're able to see which machines are consuming more or less energy over time and hence spot a trend. Now, when we look at the outcome of this client, when we brought in our solution, what were the outcomes that they experienced? Well, first of all, we helped them identify a resonance issue on variable speed water pumps, motors. Secondly, because we were able to identify that through the maintenance action, they were able to prevent water pump downtime, and they were also able to reduce 20% energy consumption by prioritizing maintenance based on the energy insights, not just waiting for the machines to break, but going, hey, there's an extra energy consumption, we're also going to take care of that through the same intervention. And now when we look at how, more in details, without going too many details, how we're able to spot it. So this is a trend of vibration over time. You can see there are 3 distinct events here, one at the beginning, one in the middle, and one at the end, where there's some abnormal vibration patterns, right? Typically, this is typical resonance, but then when you start looking at comparing this chart underneath vibration change with energy change, you see there's a corresponding correlated energy consumption variation in those events, right? And when you bring in at the end the speed, and typically between 700 and 740 RPM, that's where resonance in this case is present, you can see how it all comes together. So when the speed is reached in that threshold, there's an abnormal variation of energy, which creates an abnormal variation, there's an abnormal variation of vibration, which creates an abnormal vibration of energy, and hence the correlation between a maintenance intervention and the impact you can have on reducing energy, right? So at the end of this project, again, what is the conclusion? We were able to deliver 20% energy savings, 20% reduced CO2 emissions, and an overall improved operational efficiency and profitability for the client. So thank you. There should be a thank you slide, but it's not there. There you go. if there's any questions, thank you for listening.